I'm going to talk about the cosmic distance ladder, and just as a quick one, do stick with me. This is science, physics, okay? And I was quite impressed with Terence Tao's maths. Always have been, to be honest. But I came across this, and I just thought I'd talk about it briefly for the kind of science shows that I'm going to be doing. So I'm going to talk about the cosmic distance ladder, and once again I was prompted to do this after getting into yet another debate with a person that has almost zero knowledge about maths or cosmology, physics, and they'll argue with me armed with very basic facts and fixed ideas which I find annoying, especially as they equate it to being knowledgeable about cosmology and mathematics, and it really isn't so. So before getting into the cosmic distance ladder, it's worth clearing up this geometric anomaly, okay? It's often said that a sphere is the only surface whose projections are always perfect disks. And in simple terms, if you shine a light on a solid object and look at its shadow from any direction, and only a sphere appears, it will give you it gives you a circuit, and it gives you a circular outline, then it means that it's a circle. And that statement is essentially true with one caveat. It applies to solid convex shapes. If a shape has dents or irregularities, then the claim breaks down. But among smooth convex bodies, the sphere is unique in this respect. And that's one of the reasons it appears so often in physics. It behaves cleanly and predictably from every angle. Now, that idea connects loosely to how we think about the Earth, right? Because ancient observers didn't have satellites or modern instruments, yet they built a strong case that the Earth was not flat. The way ships, disappear with their hull first over the horizon, was the first kind of clue, and it left the mast visible a little longer. And it's a subtle but consistent clue that the surface curves away. And it's not true in all cases. It's sometimes just a resolution of our eyes. People claim that a ship sunk down, but if you look through a telescope, you can see that it's still there, all of it. And more striking is the work of Eratosthenes. Eratosthenes, who compared shadows of sticks in the ground in two cities, in Alexandria and Syene, and used basic geometry to estimate the Earth's circumference. Now, once again, he'd done this with impressive accuracy, but it shows that there's a curve. But it doesn't necessarily show that it's a globe. And the figure that he used was 5,000 stadia, which was their unit of measurement at the time. And a stadion wasn't a fixed global unit like a kilometre. Depending on which version you use, those 5,000 stadia come out to roughly 800 kilometres. And if you use a commonly accepted Egyptian stadion, it's 157.5 metres. And this actual straight line distance between Alexandria and Syene is in that ballpark. So he was working with a pretty solid estimate for his time. And what's often missed is how he got that number. And he likely relied on survey data from Bematists, who were professional distance walkers used in the Hellenistic world, or he used caravan travel estimates along the Nile route. So it wasn't precise in a modern sense, but it wasn't guesswork either. And these are the details that people also neglect, which make my conversations with them similar to talking to 7-year-olds. Somebody actually said to me recently, you always talk about the same things. Yes, because you're my limit. If I talk about anything else, then you're lost. And, I sound boastful today because why not every now and then? It's the areas that I've studied, and talking to people who haven't studied those areas, who just want to keep boasting and ego showing and shouting at you because of some facts that they looked at, which are dated, by the way. It's just annoying. Anyway, the arguments that I just expressed, they show that there is curvature, not necessarily that there's a globe. But turning that into a precise claim that the Earth is specifically spherical, I knew I was going to have trouble saying it, that the Earth is specifically spherical, requires an extra step, one that came later through astronomy and physics, and one that people I usually debate with, have no idea about. But I'm not a tattletale, so go study. So, moving forward, that brings us to a much larger problem. How do we measure the distance in the universe? Now, the cosmic distance ladder is that method. And the cosmic distance ladder is a method that astronomers use to answer that question. Let me explain. These are the facts already. Baby, I want you to know. So, There's no single tool that works across all scales. Instead, we build distance measurements step by step. And each method relies on the previous one, like climbing a ladder. And at the nearest level, we use parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against a background of more distant stars. And by measuring that tiny shift and applying basic trigonometry, we can calculate how far away those stars are. And this is the most direct... And this is the most direct method and reliable method, but it only works for relatively close objects. They go further by relying on standard candles, objects whose brightness is known. One important example is the Cepheid variable stars, and these stars pulse in a regular way, and the period of their pulsations tell us their true brightness, and by comparing how bright they appear from Earth to how bright they actually are, then we can work out their distance. And beyond that, supernovae become useful, and these are the stellar explosions that reach nearly the same peak brightness every single time. And because they're so bright, they can be seen across vast distances, allowing astronomers to measure galaxies far beyond the reach of the parallaxes of Cepheid stars. And at the largest scales, redshift comes into play. Light from distant galaxies is stretched as the universe expands, shifting it towards the red end of the spectrum. And by measuring this shift and applying what's known as Hubble's law, we can estimate how far away those galaxies are. And this step connects distance to the expansion of the universe itself. And each rung of this ladder depends on the ones below it. If the early steps are slightly off, the error carries upward. And that's why there's an ongoing debate in cosmology, particularly around the exact rate of cosmic expansion. Different methods don't always agree perfectly, which suggests either hidden errors or gaps in our understanding. And this is where a mathematician like Terence Tao offers a useful perspective. Now, Tao isn't a cosmologist, believe it or not, but he's often emphasised the importance of rigour, clarity and checking assumptions, especially in complex systems built from many interdependent parts. Now, Terence Tao is one of those rare figures who sits right at the top of modern mathematics. He was a child prodigy, doing university-level maths as a kid, and he went on to become a professor at UCLA in his early 20s. And his work isn't in just one lane either. He's contributed across many areas like number theory, harmonic analysis, and partial differential equations. And the cosmic distance ladder is exactly that kind of system I described earlier. It works, but it isn't a single clean equation. It's a chain of reasoning, and every link has to hold. So the broader point is this. From measuring shadows in ancient Egypt to tracking the light of exploding stars billions of years away, the method hasn't really changed in spirit. We observe patterns, build models, and extend them step by step. But the further out we go, the more we're relying on layers of interpretation rather than direct measurement. And that doesn't make the system unreliable. It just means that we should understand what it is, a constructed framework, not a single decisive measurement. And like any framework, it's only as strong as the assumptions holding it together. And it's much more than throwing single facts around, claiming to know how it all works. I am Neo PG.